Next, we'll consider this problem. A 12 microfarad capacitor is connected to an AC source with an RMS voltage of 120 volts and a frequency of 60 Hz. We want to know what is the RMS current in the capacitor. So we know that the RMS current is related to the RMS voltage by the voltage of a capacitor RMS is equal to I RMS times the capacitive reactance. So if we want to solve for the current, the RMS current is going to be equal to the voltage RMS across the capacitor divided by the capacitive reactance. Now the capacitive reactance is 1 over 2 pi FC, and if we take 1 over that, we'll find that the IRMS is equal to the voltage across the capacitor RMS times 2 pi FC. So we have all of those quantities, we can plug them in. The RMS voltage across the capacitor is going to be 120 volts. And then we have that multiplied by 2 pi. The frequency is 60 Hertz. And then the capacitor has a value of 12 microfarads, so 12 times 10 to the minus 6 farads. So that's going to give us an RMS current which is equal to 0.543 amps, so about half an amp. What happens if we connect an inductor to a circuit? Well, we remember the thing that an inductor does is it opposes the buildup of current. And because it opposes this buildup of current, the voltage is actually going to lead the current by 90 degrees. So it's the current that will lag behind the voltage. We also know that inductance follows this relationship, that the voltage of an inductor is equal to the L, the inductance, times the change in inductance divided by time. And this indicates that a change in inductance with time is equal to times the inductance, and that's going to be equal to the voltage across the inductor. This indicates that the voltage across the inductor is proportional to the slope of the current versus time graph. So since delta I time over delta t is proportional to the voltage, then the voltage depends on the slope. So if we look at this graph, we can see that when the slope of the current is maximum, when it's the steepest, and when it's positive, that's when we have the maximum voltage. When the slope of the current is 0, that's when the voltage is 0. And when the current has a negative slope that's steepest, that's when the voltage is minimum. Now we can also write down an Ohm's law-like relationship that gives us the relationship between RMS or maximum voltage and current, and instead of the resistor value, we have something called the inductive reactance. So the inductive reactance, like the capacitive reactance, depends on the frequency, but it's equal to 2 pi times that frequency times the inductance. So we can also write down relationships between RMS voltage and RMS current, or maximum voltage and maximum current, and then the current gets multiplied times this inductive reactance. So next, let's consider this example. In the inductor of a 60 Hz AC series circuit, the peak voltage precedes the peak current in each cycle by what time interval? So we're told that we have the voltage preceding the current, and we want to know by what time interval does it precede. So both of the current and the voltage are represented by sine waves. And if you think about a sine wave, A sine wave looks like this. And this is 0. And if we're plotting the sine wave versus angle, then 180 degrees is here. This is 180 degrees, and this would be 360. So in 360 degrees, or 2 pi radians if you prefer, the sine wave undergoes one complete wave, one complete cycle. So we know that the voltage precedes the current by 90 degrees. So voltage precedes the current by 90 degrees. So if we look at this graph, then 90 degrees is going to be here. And so this is by how much? This is 90 degrees, which is the same thing as pi over 2 radians, since 180 degrees is pi, 90 degrees is pi over 2. So this is by how much? This is the angle by which the voltage precedes the current. And we want to change that angle into a time interval. The clue that we're given is that the frequency of the power supply is 60 hertz. And we know that hertz, so 60 hertz, is equivalent to 60 cycles per second. So what we have is, we know that this the one precedes the other by 90 degrees. So 90 degrees, and according to our graph, 90 degrees, well, if we have 360 degrees, that's equivalent to one cycle. So a full 360 degrees is one complete sine wave, one cycle. And because of the frequency that we're given, we know that 60 cycles occur in 1 second. So the frequency allows us to go from cycles to time, from cycles into seconds. So this is basically like a unit conversion. So we have started out with degrees, and that's the angle by which the voltage precedes the current. We can change it to cycles, and then we can change cycles to seconds using the frequency. So then this is equivalent to 4.2 times 10 to the minus third seconds. So that means that the voltage will reach its peak before the current by 4.2 milliseconds. Now we can have a circuit with a resistor, an inductor, and a capacitor all in series with an alternating current source. The current at every point in this circuit will be the same, and it will be oscillating like a sine wave. But one question we'll want to ask ourselves is, we know the current everywhere is the same. What's going on with the voltages across the resistor, the inductor, and the capacitor? So how do the RMS voltage quantities compare with each other, and how do we find them? Now, the instantaneous voltages across the elements follow the rules that we stated previously on previous slides. So what we saw was that if we have some oscillating current, that the resistor, the instantaneous voltage across the resistor, is in phase with the current. So it's doing the same thing at the same time that the current is. We also saw that the voltage across the inductor leads the current by 90 degrees. So it peaks before the current does. So all of its peaks come before the current peaks. And the voltage across the capacitor lags by 90 degrees. So the voltage across the capacitor it peaks after the current does. So now the question becomes, how do we add these voltages? If you know the instantaneous voltage across the resistor, the instantaneous voltage across the inductor, and the instantaneous voltage across the capacitor, and you wanted to find the power supply's voltage, you could just add them up. That works for instantaneous quantities. But if we're measuring the voltages across these circuit elements with a multimeter, the multimeter doesn't give us instantaneous quantities. It gives us RMS quantities. And the RMS is an average. And we can't just add up RMS quantities because we can see that with these instantaneous voltages, some of them cancel. So the voltage across the inductor and the voltage across the capacitor, they're doing the opposite thing, and they'll partially, at least, cancel each other out. And how do you add all of these sine waves together anyway to figure out what the voltage of the power supply would be if you measured the RMS voltages of these different elements? You're just getting a kind of average, and that kind of average can't just be added together because these sine waves partially cancel with each other. So how do we go about adding RMS voltages and maximum voltages? And the key to doing that is using a tool called a phasor diagram. And the phasor diagram keeps track of the fact that we have sine waves that we're adding together, and they're shifted with respect to each other. They have different phases, and because of that, the voltages of the inductor and capacitor, for example, will at least partially cancel. So the way a phasor diagram works is that you represent each voltage with a vector. And these voltages are either maximum quantities or RMS quantities. So you either make an RMS phasor diagram or a max voltage phasor diagram. So for this example, we'll use maximum quantities, although you could just as easily do it with RMS ones instead. So the way you make a phasor diagram so that you can add up voltages correctly is you draw the voltage across the resistor, which is in phase with the current, along the positive x-axis. So the positive x-axis represents the current direction. Then the phase offset is the angle with the positive x-axis. So since the voltage across the capacitor leads the voltage across the resistor, then the voltage across the capacitor is drawn at negative 90 degrees from the voltage across the resistor. So it's written in the minus y direction. The voltage across the inductor lags behind the voltage across the resistor, and so we draw it in the positive y direction. Then we add up these three vectors as vectors to find the voltage across the source, which is the power supply. So we would add them tip to tail, and so this would be still the voltage across the resistor. Then we slide the inductor voltage down here, so this is the voltage across the inductor, and then the voltage across the capacitor is in the opposite direction. So when we add all these three vectors tip to tail, the resultant vector is the voltage across the AC power supply. So if we then look at how we would calculate this, we can see that we would need to, if we need to find this length here, we need to use the Pythagorean theorem, and the x component of this triangle here, this leg of the triangle here, is the maximum voltage across the resistor. So we square that, and then plus, so this would be like a squared plus b squared. This is our b side, and so that's the difference between the inductor maximum and the capacitor maximum voltage, and then we square that, and then that gives us the square of the voltage across the hypotenuse of this triangle. So the voltage across the power supply follows this expression here. And we would use the same sort of expression to find the RMS voltage across the power supply. It's just that we would use all RMS quantities instead of maximum quantities. The phase angle tells us something about what the voltage across the power supply, if we were to draw a graph showing how the oscillating current of the power supply or the oscillating voltage of the power supply relates to the current in the circuit as well as the voltage across the resistor, the angle that it lags behind is represented by phi. So phi is called the phase angle, and that gives us the delay of, or the phase difference between the voltage across the power supply and the current in the circuit. So we can see that we would find this phase angle just by looking at this triangle, and so the tangent of this angle would be opposite, which is the difference between these two quantities, divided by adjacent, which is the voltage across the resistor. So we know that we can write down an Ohm's law-like relationship for all of the components in our circuit. So we can write down that the maximum voltage across the resistor is equal to I max times R. We know we can write down that the maximum voltage across the inductor is equal to I max times the inductive reactance, and the voltage across the capacitor is equal to the maximum current times the capacitive reactance. And we can write these same things down for all RMS quantities as well. What that means is we can go back to the previous expressions, the expressions on the previous slide for finding the voltage across the power supply maximum, and replace all of those voltages. So replace all of these voltages with I max times either the resistance or the capacitive or inductive reactances. Then we can pull an I max out front and we get this expression. So this is just another expression for finding the voltage of the power supply maximum, if you know the maximum current, and the resistance and the capacitive and inductive reactances. Now this quantity here that multiplies the maximum current, this is known as the impedance of your circuit. And the impedance acts kind of like a resistance for the whole circuit. It allows you to write down an Ohm's law-like relationship between the voltage of the power supply and the current in the circuit times this impedance. And once again, the same sort of relationship holds if we use RMS quantities instead of maximum quantities. So we also have a similar relationship for finding the phase angle, which is the amount by which the voltage of the capacitor, or voltage, sorry, of the power supply leads or lags the current. And we can find the tangent of the phase angle is equal to the difference of the between the inductive and capacitive reactances divided by the resistor. So one can also make a phasor diagram instead of using voltages by using the resistance of the resistor, the capacitive and inductive reactances, and representing the power supply with the impedance of the circuit. So here's another question for you. In the circuit shown, the instantaneous voltage of the source is equal to what?